All right, so let me share screen. Okay, here we are. So the next step here is, we're gonna do bash. I'm gonna navigate to the desktop. All right, so I'm going to create a new directory here. Just going to call it sklearn examples. Okay, so we're going to look at some data sets. Let's see now. All right, so let's create a script. Call it machine learning code. What? Oh. I'm sorry. Thank you. Good catch there. All right, so here's the screen now. So we're going to create a script, machine learning code.py. All right, and we're going to import from sklearn, import data sets. Test this out. All right, so it runs. So we have sklearn available. We don't really need to use the Conda environment, I don't think, but let's do it. So let's activate PyTorch. Let's run it again. All right, so we have, it runs, so it finds the libraries. So let's go back to the script now. Let's just add a few libraries that we might need in here. So let's do import NumPy as NP. We'll need some metrics for this one. So from sklearn dot metrics import. So we're going to import the confusion matrix. And also the F1 score. So we're going to import the F1 score. All right, and then we can add a few more later. So the first thing we're going to think about is, let's see. Let's load some data. Let's load the iris data set. Okay. Let's do load. Iris. So we're going to say iris equal data sets dot load underscore iris. Okay. And then we're going to break this up into X, the X data, and the Y vector. Okay. So let's go over here. And in here, it should be iris.data. We're going to slice it and say all rows. But we're going to just say columns 1, 2, 3. Now, iris should have 4 columns, right? So one thing we should probably do before is print out iris. So we can get a feel for it. All right, so let's go ahead and try this one out. All right, so that's Fisher's iris. You can see here we have target data is in target, and then the X data is in data, and it's got 1, 2, 3 columns. Okay, so we need all 4 columns, so it should be 0, 1, 2, 3, right, for the 4 columns. So let's go back to the script. You can read through this, by the way. But remember, this is Fisher's iris data set from his experiments. There's quite a little bit of detail there, but we're familiar with this data set already. So let's go back to the nano script. If we wanted just 3 columns, we would just do something like this, but we want all data basically, right? I'm gonna take out the print statement, and instead I'm just gonna do this. So now we can print these out individually. So for instance, I'm gonna do print Y, right? So let's take a look at that one. And there's the labels, right? So we know in Fisher's iris, there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so there should be 150 there. All right, so now we can also print out the X data. And there it is. So we have X and Y, right? And now we're going to use that data to train a couple of machine learning models, basically. But we have to follow our pipeline as well. Okay. So let's think about that. Let's start with just creating a classifier, right? We're going to create so if you remember, you did this in Weka, right? So when you guys played around with Weka, what were some of the supervised learning algorithms that you used? What were their names? Naive Bayes, that's one. What's another one? Nearest neighbor, KNN. What's another one? Which is what? Decision trees. Yeah. What's another one? A multi-layer perceptron, right? Which is basically the family of like neural nets, but not the same framework, but just not, you saw how slow it was. So implementing it as a deep learning algorithm, it's not efficient in Weka. Yeah, exactly. Did you see one that was called random forest? So random forest is basically an algorithm that uses several decision trees together, right? So it's usually a little bit better. So anyway, so like I said, if you guys have an interest in learning how to implement those algorithms a little bit more from scratch, I recommend that you take ITS 365, which is the foundations class, which covers the algorithms themselves. Here we're more on an applied level, just trying to apply it to data sets. But so let's take, so you know how to apply it. You know how to apply these in Weka, right? Now let's go ahead and try to create the random forest machine learning object or algorithm in sklearn. So using the sklearn library. So let's take a look. So we're going to go down here. And usually when you're trying to implement these kinds of things like a random forest or a decision tree, you will come from, for instance, to sklearn. Sklearn will be your kind of the place to go look at that. At the end of the day, it's not necessarily the algorithm that's the most important. At the end of the day, the most important thing to have is the data. That's why data is king. That's why, as I said, Google has enough cash to buy Boeing twice over. So the data is what matters. All right, so let's go ahead and let's think about the logic. So we're going to set up a function here with sklearn for this. So random forest. Okay. So random underscore forest. I'm just creating a function here. All right. And these are my own functions. For this, I'm going to want X train, Y train, X test, Y test. Now you already know how to do these, how to get these. You know that we have to get them from Iris, right? So Iris needs to be converted into train and test set. So we'll have to do that step. 1, 2, 3, 4. So here I'm just going to plug in the libraries here basically. So I'm going to say from sklearn dot ensemble import the random forest classifier. Okay, so there it is. And then once we have the object, then we can just proceed to create. Once we have the module, we can just proceed to create an object of that type. So I'm going to say forest equal random forest classifier. Okay. And then we're going to need to provide some parameters here. Usually just default is fine. So it's going to be the criterion for splitting. So a decision tree is basically, as the name implies, right? You get to a node, you grab one of the features, one of the 4 features in Iris, let's say feature 3, and you grab it, it's important, and you say, okay, you know, if the value is less than this, I go in that direction. If the value is more than this, I go in that direction. And then in the next node, it's another feature, maybe feature 1. And then you say again, if it's less than this value, I go in this direction. And that's how eventually you will end up at a decision. You guys see that? So the criterion for doing that is based on an area of statistics, right? And there's several techniques associated with that. One is called information gain or entropy. So basically ideas that are a little bit related to information theory. But at the end of the day, they're more like probabilistic things related to frequencies. You see frequency of the features in the data, etc. And so we're not going to get into the details of entropy here, but that's one of the criterion that you can use to make the decisions, basically, in the algorithm itself. So we're going to specify here entropy. And then we're going to say n estimators n random state equal 1. And usually you don't have to change the number of jobs equal to. All right, and now we have in here basically the object initialize a random forest object. 1, 2, 3, 4. And now you're going to say forest dot fit. So usually when you say the call the function fit, what that does, we've seen this before, I think, when we applied it to singular value decomposition. Remember, when we were doing compression, the idea is the functions are fit, predict, transform, and then fit predict together so that you can just like in one do the whole thing, right? But in this case, we just do fit because this is the equivalent of the training, right? Like when we were doing the train loop in PyTorch. So here I'm just going to say X train, and then comma Y train. Okay. And then once we have trained the model, we're going to predict some labels, right? So in that case, we do forest dot predict. And what do we use to predict? What goes in here? X test, very good. So X test goes in there. And now we are basically ready to do the, we've got our Y pred. Now we need to measure performance. So what we're going to need here is a function that prints our performance metrics. So I'm going to say print stats percentage, or let's just say print stats performance metrics. Okay, so obviously we need to create this function, but it should be pretty easy. So this function will just take, we'll take an input, which is just the algorithm that we are, so that we know. So in this case, for instance, random forest. Okay. Then also we need to specify the criteria to compare, right? So in this case, it's going to be Y test, which is the real labeled data that's provided here, right? But also the Y pred. Right, so these two are going to be compared as metrics to see if we did okay. So for now, let's go ahead and define these, right? So we have some things to define. We need to, first of all, define this function. We also need to split this data, right, so that it's available. So let's go ahead and do that here so that we can test out our script. All right, so then we need first of all, we're going to split our data, which means we need the train test split. Do you guys remember that one? So that's a tool, a module that we learned about before. So let's just add it in here. So from sklearn dot cross validation import train test split. Okay, so we have that in there. We're also going to want to normalize our data. So let's do from sklearn dot pre-processing, and we're going to import the what is called the standard scaler. We've seen several ways of normalizing the data. Remember, you should normalize your data. Okay, so we talked about that before. So we've got the standard scaler in there. And let's just make sure that we have all the metrics that we need. So we did F1 score. Let's also do the recall score, precision score. So that's recall, F1 measure, precision. We already had the confusion matrix. Do we need anything? Oh, the accuracy score, right? Make sense, guys? So these are the built-in modules for this. And finally, let's also include pandas just in case. So let's do import pandas. We have used that as well in our previous examples. All right, so now that we have all of our libraries, the first thing we probably want to do is let's actually create a normalization. So we need to call train test split. So we call this function train test split. And we're going to plug in here X and Y, right? So X is the data with the corresponding Y. For Iris, remember that these are kind of mapped together. So it's, it should work. And then we're going to specify what we want the test size to be. So in this case, I'm going to do 30% split. So 0.30. So that's 30% for test, 70% for train. Okay. And we can specify a random state so that we can always get the same randomization. In this case, random state equal any number. So let's say 0. All right, so now that we have that, remember that train test split, then it's going to give us exactly what we need, which will be in this order, X train, X test, Y train, and Y. So at this point, we have our data in perfect, exactly as we need it. You see that? We have our data exactly as we need it. Next thing we want to do is we want to do the standard scaler. So after we've split it, remember, we normalize it. So let's here say normalize. Okay, and we're going to create, this is, remember, this only applies to the features. So it's feature scaling. We don't scale the labels. So feature scaling. And we're going to say SC standard scalar, right? We call that object. And so we initialize SC as a standard scalar. And now we're going to fit it or train it on the train X data. So we're going to say SC fit X train and after we've trained it, we apply it basically to both X-train and X-test. So we're going to say here X-train normalized and also X-test normalized. Do you guys see that? So in here, all we have to do is call SC dot, and now we say transform. So we transform the original X-train into X-train normal. And we're going to do the same for the test data. So it's going to be transform X. And that's it. At this point, we are ready. We are ready. So the next part is, we've done the basic two things that we should do with our data. We've split it. We've split it into train and test, and also randomized it, shuffled it as we did with PyTorch. Then we normalized the data here. We have our function, and now we make a call to that function. So we're going to call it. We're going to call random forest. So we're just going to go down here and say, make the function call basically. So we do random forest RC. And the inputs are going to be, well, we have to look, I guess, at how we set it up. So we set X train, Y train, X test, Y test. So then here it's going to be X train, Y train, X test, Y test. Do you guys see that? Is this making sense? Pretty easy, right? So this is a very easy way of doing machine learning, actually. Just keep in mind, we normalize the X's, right? So we actually have to use X train normalized and also X test normalized. Got it? All right, so we are almost done now. All we have to do is create that performance metric function. So we want to define that. Let's do it here, I guess. And we called it print stats performance metrics. Print stats performance metrics. Do you see that? So this takes the name of the algorithm, and then it takes Y test and Y pred. Okay, so this takes name, Y test. Is that me that's making it? And then Y pred. Okay, you guys see that? So here we have the two parameters. We're going to evaluate them. So now 1, 2, 3, 4. And we just need to define this function, okay, for our performance metrics. Let's go ahead and find it. All right, so let's go ahead and do. So we're going to print the algorithm first. We might actually want to print out like some line separators. Okay. Now we're going to print the name of the algorithm. So in this case, it would just print out random forest. Okay. Now we're going to print the results for accuracy. So we can just say accuracy percentage. So a format string. And then accuracy score. And accuracy score is the module we just imported from sklearn, and it takes in as input y-test, comma, ypred. Is this clear, guys? All right, so I think now we have everything that we need for this to run. Okay, we can still add more later, but let's just see if it'll run. Okay. Oh yeah. It should be a variable. Okay. Learn cross validation. I think we did train test split before, right? Do you guys remember where we did it? Where we used train test split before? Okay, yeah. So that was so here, right? Model selection. All right, there it is. And accuracy is 98%. You guys see this? Guys, you can always print out the predicted labels and also the real labels and look at them yourself, but does pretty well, which is expected, of course. It is random forest. It is Fisher-Apfel. Any questions? All right, so let's then kind of continue on this with this same idea. So now let's add a few more metrics to that function. All right, so let's go ahead and do all right, so we've got the algorithm, we've done accuracy. Let's now do the other ones, precision, recall, and F measure. Precision. Precision score. Again, white test, white Pred. We're comparing them. Okay. Then we're also going to do recall. And that's going to be a recall score. That's white test and white Pred. And then finally, we're going to do F1 measure. F1 measure format string. So this is the F1 score. And again, white test. White Pred. Now this function is very handy and you can use it, even with PyTorch, etc. But here we're seeing it in this context. So let's try it again. Oh. Right. Okay. So here the problem is that we have to tell it they're not binary, correct? So the question is, by default, it's expecting a 2-class problem, but we're using a multi-class because there are 3 labels in Iris. So it should be in precision. So just say average equal weighted. So average equal weighted. Average equal weighted. All right, so let's try that one. Yeah, and now it's giving us the same error, but with recall and F1 measure. So we have to do it for all of them. All right, so let's make that modification. All right, so that hopefully will fix it. Again, and there it is. So as you can see, the scores are pretty good: accuracy, precision, recall, F1 measure. Obviously, this is a well-balanced data set, so there are no problems there. Any questions? Yeah. Yes. So the standard scalar is just a normalization. So in sklearn, this is pretty easy. We just create a standard scalar object. We fit it on the X-train data, and then that SC that has been trained now is used to transform X-train and X-test, basically. Got it? Other questions? Nope. All right. So the last thing we want to do in this print performance metrics is we want to print out the confusion matrix. So for that, we're going to use conf_met equal so confusion matrix which will take Y test and Y pred. And then we can print it out. Let's go ahead and run it. There it is. If you notice, remember with the confusion matrix, we want all the values to be in the diagonal. And so here you can see there's one misclassification in the test set, but just one, which is pretty good. Is this clear, guys? And remember, it's a 3-class problem. Okay, so we've done, we have now our nice performance metrics function, which we can just use for everything else. We're just using Iris. We're looking at some classifiers. So let's try a few others. So here, let's add another one. Let's think about this one. All right, so let's just do KNN, given that that's usually a very simple one. So KNN C. So here again, X train, Y train, X test, Y test. But we want the normalized data here. Normalized and normalized. All right, so again, we're going to invoke basically the module from sklearn dot neighbors import KN for K neighbors, basically. Okay, so that's our module basically for KNN and sklearn. So now we're going to do KNN, KN neighbors, classifier. classifier. So we initialize the object, and we're just going to specify a few parameters here. We're going to say that we want the number of neighbors to be considered is equal to 5. That means it'll look at the closest 5 and it'll take the maximum label. Okay. Okay, so that's 5. Then also metric equal Minkowski. And that's just like the Euclidean distance or Manhattan distance. So they're just different ways of calculating distance in the vector space. Okay. And then finally, we do KNN.fit. What do we fit it on? We fit it on X train normalized. So X train normalized Y train. Okay. Make sense? So once I have that, that's the training part. Now we can go ahead and predict. So I'm going to do YPRED KNN dot predict. And we predict on X test normalize. Normalize, just like that. And of course, once again, we do print stats performance metrics, where this takes the name. In this case, it's going to be KNN now. And it's going to take YPRED or YTest YPRED. Just like that. All right, so let's try it. Oh, and I always forget to do this for whatever reason. We have to invoke the function. So KNN RC. And of course, we need to provide the data. Oh, actually, so I made a mistake here. So really here in the KNN, we didn't have to, that's, yeah, so this here is actually wrong. We specify those in the function call, not in the function definition. So now we can go down here and do X train normalized Y train X test normalized Y test. You guys see that? All right, so now let's go ahead and try this one out. There it is. See how nice it is now, because we can run on the same data set multiple algorithms. We can get the performance metrics. Any questions? Say that again. The number of n to 5? 3 or 5, it should be fine. You don't have to do that much, I think. But it's up to you. Just don't make it an even number, because then you could have ties, right? So some people give it 1. All right, so we did that one. Let's see what else we can do. We'll do a few others, and we're basically done, right? So this is the pipeline of machine learning. You got your data set, you split it, you normalize it, and then you call a couple of algorithms. This is what supervised learning. Remember what we were doing last week was unsupervised. So let's see. What other ones can we look at? Good, KNN. Let's try logistic regression. Remember that logistic regression is one of the ones that we implemented in PyTorch that can be implemented as a simple linear neural network with no hidden layers. But here we have an option in sklearn also to implement it. So let's add it here. We're going to do logistic regression. Okay, so this will take again X train, Y train, X test, Y. Okay, so there they are. And now, as you might imagine, so 1, 2, 3, 4 from sklearn dot linear model import logistic regression. Okay, so here we'll create an object LR, and then we assign to it logistic regression. We'll have a parameter, cost parameter, 1,000. And a random state. Zero. And here we need to have a solver, given that this is, like a neural net, right? We need to solve for the parameters. So we're just going to specify this is an algorithm, the LB FGS solver. Okay, so hopefully that one should be fast. And then once we have this, we're going to do LR fit. Fit. We fit it on X train, Y train, as we did before. And then we just get Y pred equal LR dot. So we predict on X test. And then once again, we call print stats performance metrics. Where we plug in Y test. Is this clear, guys? And as you can see, that's the general idea for these problems. Okay, so let's go ahead and run it. Oh, and I forgot to invoke it. So logistic regression. Let's see. X train, Y train, X test, Y test. And these need to be the normalized versions. Like that. Got it? All right, so let's go ahead and run this one. Oh yeah, the name, right? All right, perfect. So this one worked as well. And this is how you would go about doing your experiments, right? You would look at your data. So for your project, for instance, you have A and B. So the B one is going to be little data because you're annotating. So that should fit perfectly with sklearn. So you could just use this code to, basically provide these results. Now, will your data be as good as this one? Of course, right? Because your data is going to have, that's the whole point. That's why you looked at scraping data off the internet. You're going to be have a lot of noise in your data, right? So that's one thing that you have to deal with. Okay, so we've done random forest, we've done KNN, and we've done logistic regression. Any questions, guys? I mean, I could sit here and go through 20 machines, right? I could literally do all of them. I'm not. What I will do though is I'll give you the module calls, okay? But they're all pretty similar, so you guys can create the rest on your own. Yeah. They all need normalized. If I missed it, then that's my fault. But you should. My recommendation is you should always try to normalize your data. Okay. So in the logistic regression, you said they don't need it here because the name doesn't matter here, right? But as long as they have it in the function call, because that means we're passing the normalized data instead of the unnormalized data. You understand? Got it? All right. Yeah, so as I was saying, I could sit up here all day and just kind of go through these. I'm not. Instead, I'm just going to give you the library calls so that you can build the other functions on your own. Okay, and then test them out as well. Make sense? So, yeah, go ahead. I use the default ones, to be honest, with these. If you are going to get into the parameters, you're going to have to go online, look up the function, look, always every parameter will have a description. And then maybe you'll go into, you know, the reason why you have to change it. Here, like the one that I use, for instance, the parameter, the solver, LBFGS, it's basically because it's a fast solver. You know, so in sklearn, they implemented this so that it could actually solve more real world problems. But it's an algorithm itself that's just more efficient. Do you understand? So, you know, I'm just setting up the parameters in taking the default values, but you just have to look them up. But you know, if you look at the results, they're like 90%. So. Right? It's only really usually when your classifier is not doing really well, okay, then you might have to. One of the reasons could be, yes, the results or the parameters, but also it could just be that you have bad data. That's a very real thing, right? So that's why I keep saying, you know, data is really important to this. Sometimes if you have really good data, decision tree will do a good job for your particular problem. You just don't know. There's no guarantee that just because you have the most advanced deep neural network that you're going to do well in your problem if you have bad data. Got it? Any other questions, guys? All right, so we've covered here the libraries. We covered, we used the iris data set. And then we created the performance metrics function. We looked at KNN, logistic regression, random forest. And so that's pretty much it. So I'm going to give you just a couple of ones that maybe if you want to build this on your own, you can play with it. So let's say you want to build your own decision tree, J48, right? Like you did in Weka. You know, with this approach. So if you want to do decision tree, then you can call from sklearn .tree Actually, let's do this one because one advantage of this one is that maybe I can print out the decision tree and we can take a look at it. So let's actually do this one. I want to do this. So let's go ahead and you guys can help me out. So let's see. So let's define a function, decision trees, right? Okay. So this one also will take X train, Y train, X test, Y test. 1, 2, 3, 4. All right, so now let's do from sklearn dot tree import decision tree classifier. So then we can create a tree object. Tree. We're going to do decision tree classifier. Again, the criterion is going to be entropy. Could also be information gain. Criterion is entropy. The max depth of the tree, we're going to set it as 30. And the random state, let's just set it to 0. We have this. Now let's do tree.fit. We fit it on X train, comma Y train. And of course, now we do Y print. So that's tree.predict on X test. Okay. Now we can print out the metric. So we can do print state stats, performance metrics. And this is decision trees. So say J48. And Y test. Now this also has a handy option of looking at the tree that was learned by the model. And since we're using Iris, which is small, we might be able to get a nice insight into it. So let's see if I can do this. Let me see. So from sklearn.tree import export GraphViz. GraphViz. And then I'm going to use that export GraphViz tree, right? That's the model is in there. So the model is in there and the output file. Say out file will be tree dot. Okay, so hopefully this will give us what we need, right? So it'll generate a graph of the model itself. So let's try it out. We need to call it decision tree X train Y train X test Y test. Okay, and just we use the normalized versions here. All right, so let's go ahead and try this out now. All right, so ran, that's a good sign. We've got the J48 algorithm there. now, right? With those scores, pretty good scores. So let's see if it created. So there it is, right? There's tree dot dot. And it's of size 1157. How do I look at it? Yeah. Open with image viewer. Nope. Nope. So how do you view? You guys know of a tool for that? I know it can be done. I think we just need some function for it. And that allows you to see it? Yeah. Yeah, let me see. I believe it'll work.
So when the example I did, I had to import a PyDot and then said like it's called a graph equals PyDot graph dot file. And then in the parentheses have the file name, the dot file name. It's like basically 1, 2, 3, 4 steps. I think.
Okay. Yeah, I'm taking a look here. All right, so I found, here's a command. All right, so I'm going to try this one that I found online. So let's see if I have dot first of all. Apparently I do. So dot dash, you guys can see this. Yeah. T PNG input. No, it was, what was it called? Tree. Yeah. Dot dot. And then redirection to out to tree, I guess. Dot PNG. Let's see if it'll take. All right, took that. All right, we do have a PNG with some data in it. So let's try this again. I'm going to double click. And there it is. Perfect. So that's what a decision tree looks like, as I was saying. You know, it creates, right? Look at X3, X2, X3, X3, X1, X3. Do you see that? So it's basically doing it based on the features. There's an algorithm. As I said, these are topics that we cover in 365, right? So if you want to understand the algorithms behind these, that's the course, machine learning foundations. But, when I'm doing this, I like to show this. You can see it basically shows you steps of the algorithm. And it's got some criteria to obviously to create this tree. Got it? All right, so it's a good visualization there. So let's switch back to the terminal over here. All Right, so it is, and we ran it, right? So it ran. Yeah, so we've got results for decision trees as well. So you have 4 algorithms, I think now: random forest, KNN, logistic regression, and J48. And this is yet another, instrument or tool in your toolbox, right? So we have Weka, sklearn, plus you have, of course, PyTorch, and so on. So it's 3:26. So I'm gonna take a 10-minute break and start generating this video, and then we'll continue with the second half. We'll come back at 3:36. Okay. All right, guys. So let's start the break.